Alright, another draft physics video production and such. Pretty sure anyway. Let me just check. Is that the record button? Yeah. Alright, pretty close to it. Anyway. How come? Oh, that's probably better. That's probably better. Anyway. So yeah, comments kind of thin, so we'll do another magnetism video. And there really isn't anything. You go looking, and there's Ken Wheeler videos. you know, um, you know, and it's just so annoying because you can't really do an honest search for anything. You got to open private windows to try to avoid YouTube profiling you and deciding that because you watched one guy's video one time that somehow you want to be, inundated with any content by that person, and you don't necessarily. But anyway, so I haven't seen these crash course. I didn't, it's a lot of views, so it's been around a while. 3 years old or whatever, this video. And the whole PBS thing, which is just annoying. Their videos, who they're sponsoring, it's all kind of trivial. So crash course, it's supposed to be just the simple basic idea, and of course there's nothing in here about a mechanism. So they're basically just describing effects, and effects anybody who plays with magnets can find out for themselves. So, but let's just play it anyway, because it starts, I think, fundamentally wrong. So let's play with it.
This episode is supported by Prudential. So it's Friday.
Yeah, and they do a commercial at the end, where they do the talking commercial. They're getting paid to tell you how much you need life insurance and how at 6% interest you can make all this money if you just save. Who gets 6% interest? I mean, seriously, unless you're invested in a market vehicle, you're not going to be getting 6% interest anywhere. CD ain't gonna do that. So anyway, that's just such a pile of crap.
April 21st, 1820. A physics professor in Denmark named Hans Christian Oersted is in the middle of a lecture, and he's using a compass and an electric wire for a demonstration. He turns on the current that runs through the wire, and he notices that the needle in the compass...
Alright, so this part right here, this diagram is wrong. So, great. This isn't what happens. You don't just put a wire loop and then the compass just points to the loop. As I understand, what he discovered was essentially the motor force, which is the wire's going this way towards you. You put your compass alongside of it, and the compass always, goes flat, around. It diagrams the field. So this isn't even right or correct or useful. The compass needle has a different orientation based on how you approach a field, a wire, a loop. And the important thing to understand is that, as I sort of pointed out, if I take even just batteries and I put them end to end, in a round circle, like a wire, like the circumference of a wire, or the circumference of something with a center of gravity even, you can see that, on one side the negative end is going to show, and on the other side the positive end is going to show. And that's essentially the bias that will always exist in a loop, is that one end is going to have this positive end, and the other end is going to be showing this back end. And the rest of the loop will be, you could just say, equals out and all that kind of crap, but you can't undo the plus minus part, in the sense that this is going to be the minus side and this is going to be the plus side. So you're really just saying that no matter where I look at it from, no matter what angle I look at that loop from, that same thing is going to exist. There's going to be one side that's positive and one side that's negative, so to speak, just because of the way the magnets are lined up, so to speak. If you could see them through each other, you would see that the one that's at the median perpendicular to your viewpoint, that the ones perpendicular to your viewpoint are opposite. And that's essentially the motor effect and the creation of the right hand rule, is that no matter where you move around the wire, it always looks positive on one side and negative on the other side, a little tiny bit. So again, this is a tiny difference. I mean, you can see it on a compass needle, but it's not big magnetism. It's very little magnetism.
Starts to move, and when he turns the current off, the needle moves back to where it was. Then he runs the current through the wire in the opposite direction and sees the needle move the other way. What Oersted demonstrated that day was a fundamental discovery.
Yes, that's a discovery of what? Again, an effect. No description of how it happens. Again, so he discovered that electricity creates magnetism. Yes, important at the time, but it doesn't really do what you're saying here. Let's talk about what magnetism is in physical terms. Let's do physics, modern physics, and they still have nothing better than what Oersted would tell you. Well, it just happens.
Connection between electricity and magnetism, and it changed the field of physics forever. The relationship between...
So, just more bullshit of this hype, you know, like we weren't inevitably going to do these certain things. You know, you were inevitably going to discover microbes, you were inevitably going to do certain things, and it's not all this change the world forever kind of crap. Yes, you know, I don't know what to say. It's just the wrong way to look at it. And especially sitting from a position where you've drawn a whole bunch of conclusions about how the universe works, and you don't provide any evidence really supporting any of the elemental functions that you are claiming to take place, like the whole wave theory.
Electricity and magnetism not only explains what Oersted and his students witnessed in 1820, it also makes possible much of the technology that's used today, from hydroelectric dams to your smartphone. It even explains why Earth's magnetic...
So they're not explaining anything. So again, this is just such crap. And they haven't really proven that it's electricity that creates magnetism in other things, like, for example, the Earth. The whole eddy current thing. You're really just arguing that, okay, it's like as if there was a current, but you can sort of think to yourself and understand, well, it's not really like there could be a current, because why would the current be? How would it get located in a big conductor? How does the current know it's supposed to just do this or do some certain thing? It's this whole moving charge association. They really haven't proven that moving a charge is what makes it magnetic. What they've demonstrated is that you have to move a charge to make electricity. You know, you have to move the magnet to move the electrons. You know, that's what's been demonstrated, not that moving electrons move other electrons. But you could argue that it's sort of that basic. Of course, the electrons have to move something. But there's been no evidence that anything moves inside of a magnet. So that's the fundamental argument, is that all the movement is from the outside. Again, like gravity. There's no movement inside the Earth that causes gravity, and no movement inside the sun that causes the sun to have gravity. The gravity is force. The movement came from the field, you know, the cosmic background.
Field is essentially keeping you from being cooked alive right now, and all you really need to understand...
So this doesn't really have anything to do with magnetism, right? This whole thing like, oh, well, magnetism once saved my son, and magnetism, you know, glued the guy's tattoo, you know, his toupee to his head, and, you know, the magnetism is a hero. This isn't exactly explaining magnetism, all this hype about how magnetism's important. Yeah, we can figure that out on our own, I think.
The basics of magnetism and electricity is this.
So this is like, what, physics for 5-year-olds? I mean, obviously the subject matter is way too advanced, but yet we still have to have the little kids, you know, whatever schoolhouse rock kind of crap. It's got to be Big Bird, you know, Sesame Street thing.
probably familiar with the basics of magnets already. They have a north
Yeah, probably. Yes, that's right. And you won't give me anything extra.
and south pole. Two of the same pole will repel each other, while opposites attract.
Right. Now, why don't they think about that? See, that's what physics didn't do. They didn't sit there and say, gee, that is curious. They have this opposite effect on each other. How could they possibly do that? What are the possible ways that you could create a circumstance where you could have this opposite effect? And it's, inverse in such a way is that, you can't just explain it with one mechanism. If I take just one mechanism, I say there's one virtual photon that's doing it. Well, that just doesn't work. I somehow need two mechanisms. I need one to create the opposite of the other guy, and I need that one to create the opposite of that one if I'm going to be able to create two different effects. They could have figured all that out, but they just didn't think, didn't just look at the simple things. Sames repel, opposites attract. Those two facts need to be resolved into some sort of explanation of the puzzle. What can cause that? And if you think about it for a while, you'll figure out there's only one way to do it.
Only certain materials, especially those that contain iron, can be magnets. It depends on their molecular properties. And other metals, including cobalt, nickel and iron, are attracted to magnets, even though they aren't magnets themselves, like the metal in your refrigerator door. And there's a magnet.
So there's another way of saying it, but that's sort of not the right way to say it, right? Obviously she first says certain things have magnetism. Well, the reason why lodestone has it naturally is because of the iron. So you just basically say you can make a permanent magnet out of these three materials, and she should have just left it with that.
Magnetic field around Earth, which is why you can use a compass to figure out which way is north. The magnet in the compass aligns itself with the Earth's magnetic field. Just as we use electric field lines,
which is a tiny field, which should be pointed out that unlike a lodestone, a little tiny thing that has kind of a strong magnetic field, the Earth's magnetic field is putrid compared to the mass of the Earth.
lines to represent the electric field created by charges, we can draw magnetic field lines to represent magnetic fields created by magnets.
So they'll draw again the wrong lines. So instead of dealing with the force, it's obviously a force of some kind. It moves at a speed. They know it moves the speed of light. The same speed happens to be the same speed as light and gravity. Other things that could be called forces. And they just don't pay any attention to the core facts and attempting to explain why is that.
As with electric fields, the more crowded the lines are, the stronger the magnetic field.
So again, the more crowded the lines are. These lines are completely arbitrary, dependent on what you're using to create the line. That is, there is no, there is nothing. Unless you establish what size object, what size magnet you're going to be using, you can't establish what this line is or what it represents. But everything obviously is creating a proportional amount. And as stated, if Maxwell was to draw this for a charge, he would have drawn straight radial lines. Those would have been the lines going out from the object, like rays of sunlight or something. And crossing lines would be about how many lines do you cross, how many lines go through you at a distance, and that'll tell you exactly how. It's like the argument for the interferometer, which they never talk about. But if you diverge light, over a distance, that is, you shoot a laser beam even, the dot gets bigger the further away you go. So the light is diverging, it's spreading. And the spread of the light is proportional to the distance you are from the object. So in a sense, it tells you the intensity. And likewise, yeah.
Lines point from the North Pole to the South Pole, like how electric field lines point from the positive to the negative charge.
So here they have them moving again, like there's some evidence that something moves around a magnet, and there's no evidence that anything moves around a magnet. So they're just, like I said, they just keep selling this idea that there's a flow of something. And there's no flow. I could break those lines anywhere. I can take iron filings and I can put my finger through them and just break them all. and the rest of the filings stay exactly where they were, because they're not being controlled by some flow of anything. How else to say it? I mean, I've already explained it. They're just showing you how a magnet lines up to another magnet based on how much repulsion and attraction it's getting from both ends. So one end is attracting one end of the magnet, one end is repelling. From the other side, one end is attracting, one end is repelling, and they're exactly inverse. So of course, when the other magnet is exactly opposite the other magnet, parallel, it's going to line up parallel. But if you move it forward a little bit, well, then it's going to get more effect from this end than from this end, and so obviously it's going to start tilting and tilting and tilting and tilting towards that bias. There is no pathway. There is no anything. This is just, you're just taking isolated places and saying, how is another magnet going to line up? It doesn't represent a pathway of any kind.
But there's a key difference. You can have an electric field spreading outward from a single electric charge, but that can't happen with magnets.
So again, it's just silly because, of course, that's exactly what happens with magnets. So I don't know what to say. If you just drew the radial lines from the two ends of the magnet, okay, as black and red, let's say, and you just recognize that the black bits make one end of the magnet attract and the red ends make the other end of the magnet attract, and vice versa for repulsion, you'll have exactly the same thing. So it's exactly, this is like mock magnetism, right? So I can it's like they threw out mock gravity because they didn't want to spend any time thinking about it at all. A regular mechanical system, but it works perfect for gravity. It just has some velocity issues with this issue of drag, and I've explained that drag is a real thing because electrons and protons both experience drag. So of course there is drag, yes, but obviously some systems of atoms are capable of overcoming drag, and they do. And so here's another example where they didn't go with this simple mechanical model, just show the force being radiated, that is, as rays coming out of the object, whether it's reflected or coming out. I'm just saying, same difference. And that's all. You just see the magnet as a filter. It's just taking force that comes in, filtering it, so you get all black stuff at one end, all red stuff at the other end, and it works perfectly to describe what a magnet's doing. And now we don't have any drag problem. We don't have any catches they can escape with. But they never even considered it. They were so obsessed with their silly wave theory, they never even considered, well, what would a particle, how would a particle mechanism work for magnetism? They never even tried it.
Because you can't isolate one magnetic pole. If you chop a...
Again, the fact that you can't isolate one magnetic pole and still have a magnet. Obviously, a magnetic monopole won't be a magnet because it's a monopole. It's not a dipole anymore. It doesn't have the other pole. It can't behave the same as a dipole when it's a monopole. But quite obviously, if you were to actually describe what a north all by itself or a south all by itself, what would it look exactly like? It would look exactly like a charge. It would look exactly like an electron and a proton. So here they're declaring there's no magnetic source, there's no source, monopoles, for the dipole. Yet logically, if you just look at the evidence, of course there's a source, the electron and the proton. Of course, we already know that that's what makes an atom magnetic, is the fact that it has a decidedly north and a decidedly south side, so to speak, or attitude towards the world. It's showing itself to have that. Oh, it's pathetic. And I would argue that in the function of electromagnetism, they are still, the atoms are monopoles of charge. The atoms become charged north or charged south in the sense that the electrons become dominant or the electrons become passive. An atom isn't a bar magnet in a way. You can think of the electrons on the outside and the proton on the inside, and the two forces are getting mixed. So if you thought of the, I guess I could draw that. I suppose I could. Alright. Oh yeah, this is magnetic. I forgot about that. Oh, I better put my smoker over here. Guess I need it. Alright, so if you thought of an atom as a center and then stuff out here, you could sort of understand that as a profile, when you're looking at it from some position, you could think, okay, well, this force can get through here, and this force is coming at you this way. And so you're getting a mixture of, like, just make a squiggly line for that one instead of using two colors. So you're getting a mixture of the two, when you look at it. But you could see from another position, say if you're looking straight on to the electron, well, then you'll get this force, but you won't get much of this squiggly thing, okay? It's not as strong. So from this position, this looks negative, and from this position, it looks positive. That kind of thing. So it really just has to do, and so you can sort of understand, if I make these electrons closer, this atom will look more negative because less of the positive can get through. And the further away I put the electrons, the more of the positive that will get through, and less, and the negative proportionally be less. So you can sort of understand that the whole atom itself is becoming polarized just based on the basic polarization, that is, that it has two monopole objects in relationship to each other. But the polarization is completely dependent on perspective, because different points of view will see a different thing. Number one, that's quite possible. And depending on this arrangement, the whole atom either becomes net, okay, as a net thing. It will appear either positive, or it can appear negative, or it can appear neither, neutral, just depending on these distances. But clearly, I just stated again, they've never explained why the electron and proton aren't exactly what you would expect magnetic monopoles to look like. They fit whatever description you would have of a north all by itself and a south all by itself. That looks exactly like charge. Exactly.
Bar magnet in half, you don't end up with one north magnet and one south magnet.
Well, you do if it's an atom. So again, they didn't just say, well, if we take a magnetic atom, okay, and we cut that in half, what do we have? Oh yeah, then we have an electron and we have proton. So, this is just some nonsense rule they made up that not a real thing, okay? It's something Maxwell said, he didn't prove. It's not vital to any equation or any concept to annihilate this idea that magnetism is caused by something. So it's like Einstein forcing acceleration to be the same as velocity, which is just nonsensical.
End up with two magnets, each with its own north pole and south pole. This means that the magnetic field lines surrounding a magnet always form closed loops. We measure.
You can sort of think about this just elementally, okay? I mean, she's saying there's no such thing as the smallest magnet inside of a magnet, right? I mean, we're saying, okay, let's agree. Magnets make magnets. So I pile a bunch of magnets on top of each other and I make a bigger magnet, right? Like a bigger battery, I just make more magnetism. The more magnets I put on top of each other. Well, we know there's still a basic magnet here somewhere, right? They don't think it's infinite, do they? Do they think there's an infinitely small magnet and I can infinitely cut the infinitely small magnet into infinite little pieces? No. So they know there's a basic elemental function to magnetism, and that's the atom. And they know that if they cut the atom in half, what are they going to get? They're going to get one side that's got a lot of electrons in it, and one side's got a lot of protons in it. And they're just playing this stupid... I don't know what they're doing. They just didn't think about it.
Magnetic fields using a unit called the Tesla, which is 1 Newton per ampere meter, and 1 Tesla is a very strong magnetic field. The fields from...
So this is all the kind of stuff that who could care, and what do you need to know any of this stuff for? So she's doing this, first treating these people like the viewer's an imbecile, and then starting to talk about stuff like, what do you mean a Newton per meter squared? What does that even mean? So it was, just stuff that couldn't possibly matter.
The strongest superconducting magnets in the world at only 10 Teslas. Now, when Oersted was doing a demonstration on that fateful day in 1820, he was using a regular...
What is that sound? I guess it's on their video. So all these production values, and they have some sort of brr, 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 brr sound going on.
compass magnet. But when he brought the magnet close to a wire carrying current, the magnetic field from the current exerted a force on the needle, moving it to point in a different direction. Oersted had discovered one of the fundamental principles of electromagnetism.
So again, she has this illustration that's wrong, as I understand it. I mean, the thing that Oersted discovered is that you have the conductor going through something, and the magnets are the compass is being rotated around the conductor, and the compass does this thing, it changes its position to always be perpendicular to this. And that's not what they drew. It's not what they're illustrating.
Current produces a magnetic field. After a few more months of experimenting, Oersted figured out that when a current runs through a wire, the magnetic field that it produces surrounds the wire.
So again, they have all this movement again. You'll never get to anything. You'll never get an electron or a proton or anything to ever go like this around the wire unless you... Let's see, what do you have to do that? Alternate the current. You have to do something to create some other movement for that to happen. I'm trying to think of the right word. Well, anyway, continuing.
The field lines, the magnetic field would appear as circles with the wire at their center. If the current was coming straight towards you, the field lines would be pointing counterclockwise. And we use the vector B.
So again, it just has to do with which orientation, as I just stated. You can just understand, okay, here's the other part to this. If I have a bunch of magnets, little magnets making a big magnet, you sort of have to understand that they have to arrange themselves so they can interact with each other. So the positive end has to line up with the bottom end. So if we just use top and bottom that way. So when they're next to each other, they have to stagger to be able to arrange compatibly to stay in a small space. They can't, if they line up like this, they'll repel each other and be forced apart, and that'll break the substance, and the whole thing will fall apart. So they can't line up this way. They have to line up this way. And that's sort of what you discover, is that what do you get then? You get north, south, north, south, north, south. So not only do you have magnets lining up creating a north-south this way, right? You have some north-south, north-south coming this way, sideways. So in the wire, when electricity is going through and creating these magnets, when it's magnetizing the atoms for a moment as the electricity is transferred, what's happening is that these atoms are becoming, north-south, north-south for a very brief moment, and they're also becoming north-south this way. But that's why it's a small amount of magnetism. You have to put very high voltages, very high amperages, volume of changing of the atoms to get much effect.
To represent the magnetic field. The magnitude of the vector is the strength of the magnetic field, and the direction of the vector is the field's direction.
So again, this is the whole B and E thing, having an electric field and a magnetic field. Now, there's no evidence of anything called an electric field. You can't make electric fields. You just can't do it. There's no such thing. There's only the magnetic. Magnetism is the core. Electricity, the electric part, is something that happens between atoms. You have to have a conductor to conduct the electricity. Electricity doesn't have any other modes. And what's happening when you're doing that is you're changing the polarity of atoms. That is, you're filling them with pressure and reducing the pressure. You're making the electrons big, you're making the electrons small. And as I pointed out, that means the proton's profile changes. As the electrons are closer, the proton has less of a profile. As I make them further apart, the proton has a larger profile. You change the appearance of an atom, in terms of whether it looks positive or negative, based on how sparse or prolific the electrons are.
There's an easy way to remember how the direction of the electric current and the direction of the magnetic field it produces relate to each other. It's called the first right-hand rule because there are actually 3 right-hand rules. Just take your right hand and point your thumb in the direction of...
This is irritatingly irritating. So again, this just has to do with the one side is pushing electrons, the other side is attracting electrons. So obviously in the regular position of a battery, you could understand that this side would be pushing electrons and the other side would be pulling electrons. All right, so if I had this side first, then I would be pulling the electrons this way, and if I have this side, then I'm pushing the electrons that way, and that's the directionality. So that's the origin of the right-hand rule, is that the magnets have a orientation, and if I reverse the orientation, then the rule will be opposite.
The electric current. Now curl your fingers. The direction your fingers are curling, that's the way the magnetic field lines are pointing. And like
so it has nothing to do with the way the field lines are pointing. It has to do with the fact that the north end pushes, and so we're looking to say which way are the electrons going to go, and obviously if the north end is pushing, they're going to go away from the north end.
Likewise, if you know the direction of the magnetic field lines, you can use the rule to figure out the direction of the current in the wire. It really comes in handy.
Yeah, so says them. So again, and they associate direction of the current as the opposite of the voltage, when obviously the current, that is the volume, is going in the same direction as the pressure. So they've I suppose this works because it's broken it's broken inversely. They break one thing and then they break another and break another, just as we can get along with having plus and minus being opposite. So you can get the wrong answer and still use it. It still can be functional, but it's obviously wrong, and the whole reason why they have current going the wrong way is because they had that wrong answer, but they can fix that problem with some other gimmick. But you should just understand that if I know if you're resisting saying, well, how could they possibly have the wrong answer and how could the math still work? Well, just understand that Benjamin Franklin identified positive and negative wrong, and they can still get right answers.
Now, if a current running through a wire exerts a force on a magnet, you might expect the opposite to be true as well. That a magnet exerts a force on a current running through a wire. And it does, which is good because that's what's protecting us from harmful radiation from the sun.
Alright, so back to this crap. We have to point out how magnet's a hero again. Oh, magnets come to save the day, blah, blah, blah. It's just such bullshit.
Right now, the direction of the force from a magnetic field on a current running through a wire will be perpendicular to both the magnetic field and the current.
Alright, so this is just so obvious. So if you just stuck with the radial force in the first place, right? Rays. I'll draw this one too. But it's just so obvious. Yeah. Alright, so if they just conceded what is obvious, in my opinion, that the force is another straight line force. So the force is, from appearances, it's coming out straight. Now, I'm obviously arguing the force came from the outside and it reflects. So there's two kinds of force, I'm arguing. And so if this was an electron, what you would see, okay, is the two kinds of force coming. Oh, it's too far away. What do I do about that? Just draw it over. I don't think there's any way to fix it. Alright, I gotta remember where the end of the board is. So the end of the board is where those lines are. Alright, so put a line there, and then you'll know. Alright. So you have your object, and you have what appears to be, I'm saying, it just appears as if it's just radiating a force. And that's how it behaves. So what she just said was perpendicular. So the field line for this object, because it's round, okay, would be round. Alright, so this would be how you would draw the field lines. Like this is a 1 charge, and here it's a 0.75 charge, and here's a 0.50, and it diminishes with distance and all that kind of crap. And she just pointed out how the force is perpendicular to the field line. Well, yeah, perpendicular would be this. It would just be extending these arrows. All right, so again, you can have the wrong answer, and you can make it right by coming up with some rule of perpendicularity. But you don't need the rule of perpendicularity if you just get rid of this irrelevant bullshit line in the first place. You don't need this idiotic line. This divergent distance will tell you all you need to know. That's the only way. That's how you measure the strength, is how many of these lines will intersect me at certain locations, and that's all you need. So these lines are superfluous, and they're arbitrary anyway. So you don't need these, and you don't need this concept of perpendicular, because it's going to be radial from the source, from the center of gravity, so to speak, from the center of charge. That's all you need. So when they say perpendicular, they really mean they'll be exactly like the force lines, and the lines of force will continue to infinity, unless they hit something, just like gravity, and just like light bulbs. Okay, I mean, the light from my light, if I put it outside, the little photons will travel through the universe, and potentially, if they never hit anything, they'll just keep going forever in that direction. The little bits, the little force bits will do exactly this, and they don't need any perpendicular bullshit rule to do it. So what I was trying to point out, though, was the energy, the real force, is this idea of a plus force, a proton force, and an electron force, and they come in, and for electrons, the black stuff reflects. All right, and so you end up with something that looks all black, because the red stuff ends up leaving perpendicularly, in some direction. And obviously, what do I want to say about that? So obviously the mixture won't be identified until you put another charge in the picture. So you have to have 2 charges before you can see that have an impact. Because you can understand that all the red stuff, so for a charge all by himself in space, yes, he's leaking red and black, and you wouldn't know the difference. But if I put another charge, whether I put another charge that's red or I put another charge that's black, then you'll see the difference, because the black bits will just keep going back and forth between, so they'll end up multiplying themselves in a sense. All right, I mean, you obviously something's appearance would be it hitting you, right? That's how you know it would exist. So you can kind of sort of understand, if I'm reflecting something and we're both reflecting it, that the closer we are to each other, it'll appear to exist more often because it's hitting me more often. So it is more. Even though it's the same number of things bouncing, the closer I get, the more hits they have, so the more this force would have an impact. And if the red force every time just leaks out the side, then that red force can't get trapped in here, and it can't keep reflecting. So this will be the dominant force between 2 electrons, and exactly the opposite for the protons. And it just has to do with reflectivity. So I'm just saying that's where the energy comes from, is the external universe produces it, and the magnet just filters it. That's all that's happening. Yes, and you can just sort of understand how the electron and proton have no identity as a charge, the monopoles, until they're in proximity to another charge. So unlike gravity seems to exist whether the objects are interacting with each other or not. There's still the idea of the force, because it's only one side of the equation. But the other, it's lacking the whole reflection argument and all that kind of stuff. But obviously for charges don't have any identity. You can't tell they did something. You can't tell they're doing something until you put another charge next to them. because the only way you tell what charge you have is creating the reflections. So without the reflections, you can't tell one charge from the other. But when you start creating reflections, that's when you can tell. And you can only tell by having something, that's either by either bringing 2 protons or 2 electrons. It doesn't matter which ones in what order, but I'm just saying you actually absolutely couldn't tell that something was charged unless you're testing it with another charge. It has no charge if you don't test it against the charge. You have to be able to create the reflections.
Brings us to the second right-hand rule. This one helps you keep track of 3 directions: the direction of the magnetic field, the current, and the force. Here's how to use the second right-hand rule. Point your arm in the direction of the current, then bend your fingers so they're perpendicular to your palm. This represents the direction of the magnetic field. Your thumb, which is perpendicular to your fingers, is the direction of the force on the wire.
That noise is something they put in there for effect. Oh, great. Yeah, great. They put in an alternating current sound when you can do this with DC electricity. Great idea.
But what about the strength of that force? You can use your hands to figure this out too, but you'll have to use them to do math. The magnitude of the force from a magnetic field on a wire is equal to ILB sine theta. This equation tells us that there are 4 factors that affect the magnitude.
I hate this English crap, sine theta. Eesh. Twatty. Anyway, see again, this is where Maxwell broke, okay, physics, in the sense of separating, assuming that there's something different about the magnetic and the electric field, as if the force itself was a different thing. And the force is charge. The force is the fact that electrons do one thing and protons do another thing, and that's the only force. Now, whether you call that magnetism or you call that electricity, whether you associate charge with creating the dipoles of magnetism or associate with the monopoles of like electricity, plus and minus, it's still the same. They both have the same origin, force. And so there is no such thing as a B or E field. There's just, what are you radiating? Obviously a dipole is going to be a mixture, because it's got 2 poles. And a monopole is going to be less of a mixture, especially when it's in association with some other charged element. And the closer they are in association, the more it's going to matter. So the closer I bring 2 ping pong balls, paddles, and I've got a ball bouncing between them, it just magnifies the force proportionally by the inverse square law.
Of the force. First, there's the current in the wire. That's I. And the stronger it is, the stronger the force is. Second, there's the length of the wire running through the magnetic field. That's L. And the longer the wire is, the stronger the force is.
Well, it's just kind of obvious, right? So, yes. So these are just obvious things. So there's more water you have in a bucket, the more water you have in the bucket.
Third, there's the magnetic field B. And the stronger B is, the stronger the force. Finally, the closer to perpendicular the current is with respect to the magnetic field's direction, the stronger the force is. That's where sine theta comes in. It's maximum.
Right. So let's see. What's a good way to try to explain the more perpendicular you are, it's more of your face is going to get hit. So that's just kind of arguing that the effects can happen with this dipole anyway, if the dipole is in different positions. It won't be a dipole anymore. You'll just be seeing one end of the magnet or another end of the magnet, so it's not a dipole depending on its position.
Value is 1 when theta is 90 degrees. So the current is perpendicular to the magnetic field lines. That's when the force will be strongest. Similarly,
well, you can't be a detector, for both poles when you're only showing one. I guess it's one way to say it. Yeah.
Minimum value of sine theta is 0 when theta is 0. So that means the current is parallel to the magnetic field lines, and in that case, there won't be any force on the wire at all. Now, all of this math can help us understand.
Yeah, you can't push the electrons, right? Unless you're the end that pushes electrons is there to push the electrons. It's not the best way to say it. Well, anyway.
How we're being protected right now from solar radiation.
So again, another. Oh, magnetism is such a hero. Electromagnetism is a hero. It saves us from gamma rays and such. I mean, it's just such a. Yeah. It's just a waste of time.
The sun is constantly shooting radiation towards Earth in the form of charged particles. But luckily,
and charged in specific ways. But anyway, yes, and that will bend those particles, so they won't be able to hit us because they're going to get diffracted by the force. And so, but you'd have to say they have to be mostly negatively charged, I think.
for us, Earth has a magnetic field. Currents are made up of moving electric charges, so it makes sense that a magnetic field would also exert a force on single electric charges that pass through it. And this is...
Alright, so let's see. Currents are made up of moving electric charges. So again, this is a statement made, but it doesn't make much sense when you think about alternating current. They're not really going anywhere. So they're really just vibrating charges. And again, it doesn't matter. They're vibrating merely because the force is forcing electrons to pressurize and depressurize. The atom's getting fat, getting thin, getting fat, getting thin, getting fat, getting thin. The higher the voltage, the higher the differential between the atoms. Okay, that's all. Voltage is just measuring how, you could just think of it as a model, that all you're doing is saying how fat is the atom. You know, and you can make them atoms smaller, and you can make them atom bigger than some ground neutral.
This is exactly what the Earth's magnetic field does to the charged particles coming from the sun. It deflects them, sending them spiraling away and protecting us from the worst of the radiation. Let's suppose you wanted to find the magnitude of the force of the magnetic field on a...
So there wasn't much explanation there, right? So, you know, the charged particles have to be decidedly of one pole, and somehow, you know, that deflection has to happen for both kinds. So there was just no real explanation. You have a bunch of particles coming at you that are plus and minus, and then you have a magnet. Well, wouldn't it end up attracting some of the particles and then repelling some of the particles? So there's no real explanation for how this works as a practical matter.
Single charged particle from the sun. All you'd have to do is change the equation we use for the force on the current to account for the fact that we're talking about a single charge. The equation for the force of a magnetic field on a current says that the strength of the force is equal to the current times the length of the wire times the strength of the magnetic field times the sine of the angle.
So it's exactly the same equation as before. So
between the current and the magnetic field. Now, two of those variables don't apply to a single charge, the current I and the length L. But current is just equal to the number of charged particles passing a given point over a certain amount of time, which we'll call N.
Right, so that's just the volume. So this is, I mean, look, current is volume, voltage is pressure.
Times their charge Q divided by that time T. For a single charge, N is just 1, and the length is just equal to velocity V multiplied by time. So we can apply these two facts to our equation for force, which tells us that the force on an electric...
So somehow they went from here to here and then stopped and then created some new thing over here, I don't know, to replace variables with their new variables. But again, there's no point in... So here they're assuming they're talking about some elemental function, which is the electron. That's what they're really talking about. And they're claiming it's not somehow a monopole. Yet they're talking about it as if it's being the source of the mechanism. Like you can't have the mechanism without the electron. So they're considering the movement of the electron as the mechanism that creates this force, and yet they won't concede that the bipole is made out of electrons and protons.
Charge moving through a magnetic field is equal to Q divided by time multiplied by velocity times time times the strength of the magnetic field times the sine of theta. These two t's cancel each other out, so the equation simplifies to F equals QVB sine theta. That means that, like the force on a current running through a wire, the force on a single electric charge depends on 4 factors. One is the same as with a current. The stronger the magnetic field, the stronger the force. The other 3 factors are slightly different from the case with a current. First, the force is stronger the closer to perpendicular the charge's velocity is to the magnetic field lines.
So again, these aren't magnetic field lines, they're lines of force. And so obviously the closer you are to the thing producing the magnetism, the more the electron's going to be affected by it. Duh. And again, the orientation of the magnet makes a difference in terms of if you're pointing a south pole, the electron's going to fly right into it. And if it's north pole, then it's going to fly away. Whether it's going to fly, where it's going to fly, how fast it's going to move away depends on how much of the north pole you're exposing the electron to.
Means that if the charge's velocity is parallel to the magnetic field lines, there won't be any force on it whatsoever. Second, the more charge the particle has, the stronger the force. And third, the faster the particle is moving, the stronger the force. Finding the direction of this force is where the third right-hand rule comes in. So get your right hand out again, straighten your fingers with your thumb stretched outward, then point your arm in the direction of the particle's velocity. Then bend your fingers to make them point in the direction of the magnetic field lines. This is where things get a little tricky. If the charged particle is positive, your thumb is pointing in the direction of the force.
Right, and there's an assumptions built into all of these that associate the north end of the magnet with the negative charge and the south end with positive, and that's the assumption.
But if it's negative, the force is pointing in the direction opposite your thumb. So electric currents create magnetic fields, and magnetic fields exert forces on electric currents and charges.
Again, electrons are affected by magnets. Yep. That's all you got to know. That a magnet will push an electron. The north end of the magnet pushes electrons away, the south end attracts them. There, done.
Oersted's experiment was simple, but his discovery linked 2 major fields of physics and inspired other scientists to do a lot more experimenting. Today you learned about...
So again, and this is like the discovery of the round wheel or something else. It's like sort of inevitable. I'm not saying that don't give the guy credit. I'm just saying all this hype is just unnecessary for just a basic elemental function. It's somewhat surprising that there were like literally, it took like 100 years, from one discovery to another. And you're saying, well, why did it take so long?
Magnetism and the magnetic field created by a current running through a wire.
But just sort of figure out why it took so long. It's because they make these assumptions and they stick with them, and they keep forcing the new information to fit their old model. And they just keep doing that, and so they can't evolve their understanding because they keep trying to force everything to fit a model that's wrong.
Also talked about the force from a magnetic field on a current running through a wire and on a single charge.
Right, you did nothing to explain where a magnet's energy comes from. So there was no honest statement here saying, well, it's kind of obvious that there's movement happening. In the sense that magnets are creating some kind of thing, some sort of energy, because when I move the magnet, that field pushes on something, so it's doing something. It's I don't know, but there's no explanation. There's clearly energy in the sense that I just bring them in proximity to each other, and they'll either repel or they'll attract. And that repulsion and attraction isn't accounted for. There's no mechanism for it. Nothing explaining where the energy to make something move comes from. But obviously, as I'm stating, there's no static force coming from a magnet beyond the force that already exists in the field. You're just changing that force. Filtering it. Magnets are just a filter. That's it. When you magnetize a wire by putting electricity through it, the electricity it's a byproduct of the flow of electricity. that you change the shape of the atoms, and it's changing the shape of the atoms that makes them magnetic, which makes them a filter. But the electricity is not creating the magnetism. It's causing it. But the magnetism, like gravity, is coming from somewhere else. It's not coming from, gravity doesn't come from inside the earth, and it doesn't come from inside the sun. It doesn't come from the atom. It's coming from the outside.
Moving through a magnetic field. And we went through the 3 right-hand rules. Thanks to Prudential for sponsoring this episode.
I don't know exactly why they index videos after you've done the video, but whatever. So this is a little talking commercial. Just
saving a little more today, even just 1% more of your annual income can go a long way toward building a better retirement.
Right. If you save it in what? Put it in the stock market. Yeah, no. Anyway. Pathetically bad. So they're basically conceding that their life insurance, Prudential's life insurance, is just a savings program, and a really bad one. You're just better off putting the money in the bank and not bothering with Prudential at all. Anyway, yeah. Enough of a video. It's just very depressing. There's just nothing. I guess I should subscribe to this, but shit. Yeah, that's all that can be said. I guess next time I'll just do. Ken Wheeler made a preposterously horrible video on gravity. It was just, where he said absolutely nothing. Yeah, so explained nothing, said nothing, just pretended for 10 minutes to be on the subject when he wasn't anywhere near the subject. So I could play that next time, maybe. Anyway, till next time and such.